requested to deliver some lecture touching like hyperbolic geometry and arithmeticity and some number theory things, and it's very hard for me to combine all these things together. But let me first finish the proof of Oshika's for the case of the surface bundle of a circle. Okay, so this is the part dealing with the deformation theory. And then I'll move on to the rigidity part. Okay, so in rigidity part, now we're going down to the finite volume case. And then I'll try to state some general statement in general semi-simple Lie groups. And finally, maybe if there's a time left, I can focus on some surface group representations. So we'll see how it goes. Oh, also, I have to say something about arithmetic lattices. Okay, so there are plenty of things that I have to do. So I assume you all learned about convex core and limit sets and quasi-function space and so on. So the left case, which Oshika didn't deal with, was the surface bundle of the circle. It's a mapping torus case. So let me remind you first, bears simultaneous uniformization theorem. So the space of the quasi-function group, so I'm not sure this was the same notation. This is homeomorphic to a Teichmuller space of S. And rigorously speaking, I have to change the orientation. So this is a subset of AHS. Okay. So what is AHS? This is a set of discrete faithful representation in PSL to C up to conjugation. So this is discrete and faithful. Okay? Because surface cross surface is not acylindrical, this space is not compact. Okay? But sometimes if you choose a right sequence, there's some limit. So the proof of the Thurston's Haken geometrization conjecture goes like this. You choose any quasi-function group. Let me just write draw the picture horizontally. So this is a convex core, and it has two ends. It has two ends like this. So this ideal conformal structure is a parameterization coming from these things. Okay. So you choose, for example, anything like x and x bar. So these are this is a point in this picture, because this is quasi-function, maybe I should put like this. Okay. The theorem of Thurston says that if M is S cross interval modded out by x point 0 is equal to phi of x point 1, where phi is pseudo-Anasaph. Okay. So you take a product of the surface with the interval, and you glue the bottom and top by the pseudo-Anasaph map. And this is a 3-manifold mapping to us. And he proved this guy has a unique complete hyperbolic metric. So the proof goes like this. You iterate this sequence. So you begin with x and y bar, and you iterate by pseudo-analysis of map like this. Okay? So for each n, these 2 points give some unique quasi-function group. Quasi-function group. And this guy, I hope you remind that there's a Thurston compactification for Teichmuller space. The boundary was the set of projective laminations, right? And this guy, like, let's say, plus, and this guy, like this. And it's easy to show that this sequence in Teichmuller space diverge, and it converges to some special laminations. And pseudo-analysis of map has two mutually orthogonal measured laminations. Like there's some lamination. If you iterate it along phi, then it's an expanding lamination. The other direction is contracting lamination. And the property of this thing is lambda plus lambda union lambda minus this guy fills up the surface. Meaning that S minus lambda plus lambda minus, this is just a bunch of disks. It's a union of disks. Okay? And Thurston's double limit theorem tells you, so Thurston's double limit theorem says there exists a limit in AHS. Okay? It does not converge in quasi-Fuchsian space, but it converges in AHS. Okay? And it's an easy theory in semi-simple Lie group. If there's a limit, the limit of discrete and faithful representation in semi-simple Lie group is always again discrete and faithful. So this one is some hyperbolic 3-manifold homotopy equivalent to the surface. But what happens is that the picture is this. This is phi n x. This is phi minus n y bar. The volume of the convex core is getting bigger and bigger, and eventually in the limit, convex core is the entire 3-manifold, which is S cross real line. So this is called doubly degenerate. Okay? So this guy doubly degenerate, and the limit set, originally the limit set was, if you start from the Fuchsian group, the limit set was a circle, and it becomes wiggly, it becomes a Jordan curve, and finally the limit set of this group is entire two-sphere. Okay? And one can show that, you see this phi, there's an hyperbolic isometry of this doubly degenerate manifold induced from phi. It looks like periodic things. Okay? There's sort of a periodic action of phi. looks like a periodic things. So if you quotient out this manifold by this action, then exactly you come back to the original manifold. When you have to argue using some Stalling theorem that this is actually homeomorphic to the manifold that we start from. So this is the other missing part of the Thurston's hyperbolization theorems. Okay, so here the crucial thing was the characterization of the existence of the limit of some sequence in quasi-Fuchsian groups. Okay. There's some generalization of this kind of things. I'll just state the theorem. In general case, so this M is a hyperbolic 3-manifold with at least one compressible boundary S. So he defined, Oshika defined what incompressible means. So compressible is being not incompressible. So there's some curve on the surface which represents a non-trivial element in the fundamental group of the surface, but you can sort of, it bounds a disk in 3-manifold. In this case, there's some nice criterion. The theorem says, so you choose a sequence of convex co-compact, so this is 3-manifold with compressible boundary, convex co-compact hyperbolic 3-manifold with a conformal structure on S like a TI, okay, Teichmüller space S. If the points in Teichmüller space diverge, I mean, if this guy converges, obviously there's a limit. But if it diverges to some projective lamination such that lambda is doubly incompressible, so meaning, what is the doubly incompressible means that intersection number between lambda and boundary of any essential annulus or compressing disk is positive for essential annulus or compressing disk. A. Okay? So in the presence of some compressible boundary case, if you know the conformal structure or the ideal conformal structure facing this S diverges to some doubly incompressible projective lamination, then what's the conclusion? Then after passing to a subsequence, rows of I using the same notation converge. Okay, so there's some generalization of these double limit theorems. Okay, so up to now I finished the proof of the Thurston's Hawking hyperbolization theorems. Do you have any questions? If you don't have any question, then I'll move on to the rigidity part. Ushika already also mentioned that there's a rigidity theorem by Mastow. So let me recall what the Mastow theorem is. So in our case, so we are dealing with the hyperbolic 3 manifold, dimension greater than or equal to 3. And if M is hyperbolic n manifold and finite volume, so in Lie group theory, if gamma is a discrete subgroup of isometry H and O, let's say orientation preserving. So finite volume means this is a lattice. Okay. Lattice means it has a finite covolume. So suppose there's such a finite volume hyperbolic, real hyperbolic manifold, then the metric, the hyperbolic metric is unique. You see, in dimension 2, if you fix some base surface like this, by uniformization theorem, we know there are some hyperbolic structures, but we already learned that there are like 6G minus 6 parameter of different marked hyperbolic structures. You can see this by the by your eyes. Here's another hyperbolic structure. Does it look the same or different? They are not isometric to each other. Okay. But it's difficult to draw a picture for 3 manifold case, but anyway, it's a theorem. So let me state a Mastow rigidity theorem in a general context. So suppose gamma 1, gamma 2, these are some, let's say, G1, gamma 2, G2 lattices. Well, let's say just Prasad. Mastow-Prasad theorem. So Mastow proved this for a compact case, which is called uniform lattice case. And Prasad generalized his theorem to non-compact finite volume. People call it the non-uniform lattice case. Lattices in semi-simple Lie group. If gamma 1 and gamma 2 are isomorphic, as a group, abstract group, if they are isomorphic, then actually these two semi-simple Lie groups are equal, and exist some element in G1 or G2 such that these two groups are conjugate. Okay? So this is the general statement of the Mastow rigidity theorem. I forgot to tell you, G sub I is not locally SL12. It's not locally isomorphic to this group SL12. You see there is a counterexample for dimension 2 case. So lattices, they show stronger global rigidity phenomena actually. You see if you have, this means a fundamental group of this locally symmetric manifold determine the geometry completely. Okay. But let me maybe mention a history about these things. Before the master rigidity theorem, there was a theorem by Weil. So he proved Weil's local rigidity theorem as follows. So that is a global rigidity theorem, but long before Mastow, Weil, Andre Weil, he proved local rigidity theorem as follows. So Weil proved this thing. The first group cohomology of the gamma. So the gamma is a lattice in semi-simple Lie group, and the G is a Lie algebra. So adjoint action. He showed this is equal to 0. Okay, so here gamma is a lattice, G is a semi-simple Lie group, which is not locally isomorphic to SL2R. Okay, let's say inclusion. Then maybe his adjoint action looks like this. And G is a Lie algebra, semi-simple Lie algebra. I mean, what this first group cohomology measures is the infinitesimal deformation of the representations. So if you have a space of representations, say this is some space of representations like rho gamma into G, and suppose I have some point here, and if you want to measure the infinitesimal deformation at this point, you calculate the first group cohomology. Actually, this is equal to the Zariski tangent space of this algebraic variety. So if the this Zariski tangent space vanish, then you cannot deform it locally. Okay? There's no infinitesimal deformations. This was done by Weil using harmonic analysis. Okay. Then one might think of this kind of problem. Here, the crucial thing is that gamma is a lattice in this semi-simple Lie group. Okay? But we saw already that we can start off from Fuchsian group here. So Fuchsian group is here, acting on here. But, I mean, there's already a deformation inside the Fuchsian space, but we can deform it to a larger group. So this was in H2R, but in H3R, you can always deform the Fuchsian guy into the quasi-Fuchsian space. This amounts to enlarging the target group here. So originally, we look at some fixed Lie group and the lattice there. But now, if we enlarge these things, okay, like G prime, there is still an inclusion. One can ask, can we still deform inside the bigger group or not? Okay, this is the question. There are some rigidity theorem around this direction. So this is done by Goldman and Milson. So what Goldman-Milson did was this. Think of the lattice in a complex hyperbolic space. So you have a lattice. Goldman, Milson. Is it 2L or 1L? Is it? I'm not sure. Suppose you have a lattice. So this is an isometry group of complex hyperbolic space. Actually, no one gave a direct definition of real hyperbolic space using quadratic forms. We just wrote down the coordinate and matrix. But there's some N1 signature quadratic form, and the real hyperbolic space was some level set of that quadratic form, actually. And you get an induced metric. And you can do the same thing using complex numbers, okay? So you just follow the definition, but change the field from real to complex. Then there's a space called complex hyperbolic space. And take a lattice in SUN1, okay? And you can embed this guy in a larger thing, SUM1, m bigger than n. Okay? And they asked, if we look at the gamma inside the bigger one, can we deform it at least infinitesimally or not? That was their question. The answer is negative. We cannot still deform it. So this is gamma is locally rigid. Even a bigger group. That was the answer. I think this is 2L. Is it 2L? Okay. So, I mean, in their proof, they use strongly some Hermitian structure. Okay, Hermitian structure. Gamma is a lattice. Uniform lattice. Okay. After the local rigidity thing, we always deal with the lattices.
N's bigger than 1 there.
Sorry. N greater than equal to, yeah. Even for surface case, well, when n is equal to 1, this represents the complex line instead of the Poincare real two-plane. Okay. If it is just a real hyperbolic plane, you can deform it. Easily construct an example. But SU11 represents to me always a complex line. So in complex line case, you cannot deform it. That was Goldman's thesis, senior thesis. Okay. So you can ask this kind of questions in general, right? You start off some semi-simple Lie group that you like, and you embed this thing in bigger one. So if you play around this thing, there are more. You can find more examples. Shall I write down? For example, gamma SO to 1, SU to 1, there's a deformation. Okay? So this represents the real there's a deformation. But in this case, SU11, SU21, this is rigid. Basically using some Toledo invariant argument. Rigid. So let me give you a few more local rigid lattices in a bigger Lie group. So that's the list that I know of. There must be a bigger list, but so for example, take a lattice in SO31 hyperbolic 3 manifold. So take a uniform lattice in SO31 or hyperbolic 4, real hyperbolic 4 manifold. Then you can embed this thing in SP11 inside SPN1. Okay, so you are wondering what is SP11 is, SPN1. This is an isometry group of, let's say, Q stands for quaternions. Okay, so you can use the same quadratic form to define this quaternionic hyperbolic space. I mean, you have to be careful because this quaternion is a division algebra which is not commutative, but basically the definitions go through and you can define the quaternionic hyperbolic space. Okay? So first, put the lattice in 3 or 4-dimensional real hyperbolic space inside quaternionic line, and then you try to deform it, then it doesn't work. This is locally rigid. As in Goldman's example case also. Okay. Take a lattice in complex n space. Put inside quaternionic things or this. These are all a series of quaternionic type symmetric spaces. Okay. This is all rigid, locally rigid. Actually, you can put any k and m here, n plus k or n plus m, but okay. This is known to be a locally rigid. I mean, I don't want to talk about the proof, but basically you use either you follow the path of this Veil's strategy using Matsushima Murakami harmonic method, or you go to the some unfamiliar things. So developed by like Simpson, Carl Simpson, and so on. So I don't want to talk about it anymore, but we can do it. So this is, I mean, my guess is usually if you put a lattice, so this is a Hermitian type lattice inside some, well, this is not a Hermitian space anymore, right? This is not a Hermitian space anymore. But it has some kind of like semi-scalar form. There's a quaternionic 4 form and so on. And existence of such a form helps you to prove this is locally rigid. Okay. So there are two types of argument. Either use directly and brutal force using Bayes' path, or some Higgs bundle techniques here. Okay. So this is the part about local rigidity things. Then I'll move on to some arithmetic stuff. Before that, then I have to mention about modulus again. Modulus was mentioned by Oshika in terms of this some thin part. Okay, so he has a general statement about the thin part in general the Hadamard manifold. What is the modulus superrigidity theorem? Because it has an intimate connection to the arithmetic lattices. Let me mention what is the modulus superrigidity theorem. So modulus theorem holds for semi-simple Lie groups with higher rank. Super rigidity. It's super rigid, because basically higher rank lattices all looks like arithmetic lattices. So real rank of this semi-simple Lie group is at least 2. So what is the real rank? Real rank is maximal dimension of totally geodesically embedded flats inside the semi-simple, inside the symmetric space. Okay. For example, in real hyperbolic case, what is the maximal dimension of the flat you can embed? It's just the geodesics, right? So it's called rank 1. But I briefly mentioned for SL3R, if you think about SL3R mod out SO3, it's a rank 2 symmetric space. There's always a flat R2 totally geodesically embedded. So modulus superrigidity theorem tells you as long as the rank of the semi-simple Lie group is equal to greater than or equal to 2, then such a simple statement holds. You take a lattice and suppose you have some map here, homomorphism rho, and rho of gamma is everything. Okay? So you take a lattice in a semi-simple Lie group. Suppose you have a, let's say, simple, and gamma is irreducible. Irreducible lattice. Irreducible lattice. Okay? There are many equivalent definitions of irreducibility in this case. I mean, in general, semi-simple Lie group is a product of simple Lie groups. So the simplest way to define irreducibility of the lattice is the projection to each factor is dense, Zariski dense. So if you have an irreducible lattice and some homomorphism whose image is Zariski dense here, then this homomorphism actually comes from above. Okay. This is it's hard to imagine you have some homomorphism defined over like a lattice. I mean, lattice is quite dense, but also it's quite sparse. All the homomorphism actually comes from the homomorphism between two groups. Okay. So this is called Magruder's superrigidity theorem. And this, I'm not going to prove this. This implies higher rank lattices are all arithmetic. So lattices in semi-simple Lie group G of rank at least 2 is arithmetic, i.e., because I'm supposed to define this thing for Alena, I'm going to define this one, then you can use this terminology without defining this, okay? So what is arithmetic means? So basically, intuitively, what it means is that if you take some algebraic group, so algebraic group is the group defined by algebraic equations of some field, and then you take a real point of that group, okay? So if you imagine the matrix, then coefficients are real. And then you take integral point inside, okay? All the coefficients are integers now. Then it is arithmetic. That's a definition. So the rigorous definition is this. There exists algebraic Q group. Q is rational numbers, Q group. So all the defining polynomials is over Q, equivalently over integers, over Q, H, okay, such that take real point of this thing. Okay. I mean, you can define the polynomial and the solutions. You can think of the solution in any number field you want. But you just take the solution in real numbers. There is a surjective homomorphism to G. Okay. We know gamma is a lattice in G. Then you take integral point of this group, algebraic group. And this guy is surjective and compact kernel. Such that the image phi of integral points of this algebraic group and gamma, this lattice, are commensurable. Are commensurable. Commensurable means up to finite index they equal. Okay? They overlapped, and this overlapping part is a finite index in each group. Okay? So almost they overlap except finite index apart. Okay? So this is a definition. So there is some Q group H, and the surjective homomorphism with the compact kernel. If the kernel is too large, then it doesn't make any sense, because we want to say that this lattice looks like the integral point of some algebraic group. So many audiences told me it's better for the speakers to give examples rather than series of abstract definitions. So what is the trivial example here? Take a modular group. The Soyoung Cho, he drew the fundamental domain of this modular group, right? So PSL to Z. Inside PSL to R. So this is arithmetic. Why? What is the corresponding Q group? You just take SL to R. This is obviously an algebraic Q group. Okay. So you take integral point here, and this is just modding out by the plus minus identity things. Okay, so here's a trivial example, but I gave you at least one example.
Could you explain us irreducible? What is the irreducible?
Oh, irreducible means semi-simple Lie group is the product of simple Lie groups. So we don't want, something like a graph group. Okay. So that is the irreducible means if you project the lattice into each vector, then the image is statistically dense in each vector. Okay. Or maybe if you want to think of it as a manifold, you cannot pass to a finite cover so that it looks like a product manifold. Okay? Does it more comfortable? So this is a Magula's superrigidity theorem. Okay? And for completeness, I just say for rank 1 case, there's a theorem by Colette. Rank 1 case, Kevin Colette. He proved all the lattices. So let's say isometry group of, I already wrote it. So SPN1, n greater than or equal to 2, and this is the Octonian plane. There are 4 kinds of rank 1 semi-simple Lie group, and 2 are super rigid. And for real and complex case, it is not rigid. Okay? So not all the lattices in real hyperbolic and complex hyperbolics are arithmetic. Okay? Some are arithmetic, some are non-arithmetic. By the way, the arithmetic group in real hyperbolic space, SON1 case, is completely known. And I will not mention it because it's not easy to state. Maybe Alan, he will mention, or I don't know. But for complex hyperbolic case, it is hard to decide which lattices are arithmetic. So let me give you some examples of arithmetic lattices in complex hyperbolic space. Okay, so we'll apply some number theory that we have learned in the first lecture to find some arithmetic lattices. So now I assume everybody understands what ring of integers, and I think that's it. If you understand what ring of integers, there's no problem of understanding the statement. So what is the ring of integer? Ring of integer is the thing that Seohyun defined in the first lecture. So let me give you some arithmetic lattices. D is a positive square-free integer. Then you take a ring of integers inside this number field, Q. Okay, so this is a finite extension of Q, and you take a ring of integers. So let me write down the ring of integers actually. In this case, this is like Z. And D is equal to modulo 4 if it is congruent 1 and 2. If it is congruent to 3, then okay. Explicitly, if D is, for example, like 2, then you just take these combinations, right? A plus IB, you to give A, B are integers. If D is, for example, 2. This is a ring of integers. Okay. So integral coefficients. So it's a degree 2 extension. Okay. Now, you see, when we define this complex hyperbolic spaces, we use the quadratic form of signature n1, n1. So I'm dealing with n when n is equal to 2. So take matrices. Take matrices. Of the form like this. So SU like signature 2, 1 and coefficients in this ring of integers. Okay. So we have a quadratic form like this. Well, I mean the matrix like 1, 1, minus 1. So you think of the matrix satisfying, preserving this quadratic form, but coefficients in this ring of integers. Okay? This is a notation. Huh? Hermitian form, right. A standard Hermitian form. So this is a lattice. This is actually non-uniform. Okay, non-uniform mean volume is finite, but the quotient is not compact. So you can play with the different values of D, right? So there's a name for this group. People usually call this group as a Picard modular group. These are all arithmetic. Okay? These are all arithmetics. Here is a challenging problem for you. Prove or disprove. arithmetic, the existence of non-arithmetic lattice in PU like 4-1. So this is unsolved problem. People do not know whether there's a non-arithmetic lattice in PU 4-1. Okay. There are some constructions by various peoples like Masuto and Gromov and Shapiro, but for higher dimensional cases, it's difficult to construct examples. And we know the quaternion thing is rigid, super rigid. Real things is very flexible in some sense, right? We saw the older deformation theory from Oshika. Well, it's not a lattice, but anyway. There is some deformation still. I mean, as I told you, there are examples of like 3-dimensional lattices which could be deformed in like 5 or 6-dimensional real hyperbolic groups and so on. And the complex hyperbolic space is in between. So if this n is large, who knows every lattice is arithmetic or not. So no one come up with a counterexample yet. Why people study arithmetic lattices? Because it's expressed in a very simple way like this. You can use some number theory. Okay? You can use some number theory. And it satisfies all the good properties. I'll give you one property, like here's some strange number, lim. When n goes to x goes to infinity. So x log x log number of conjugacy classes of arithmetic lattices in, let's say, SL2R, the simplest Lie group that we know of, such that of covolume less than or equal to x. So collect all the conjugacy class of arithmetic lattices in SL2R whose covolume is less than x. And it is known that this has an exponential growth. You divide by this thing, this quantity. Amazingly, this converges to 1 over 2 pi. Okay. So this number has to do with some Cayley-graph things, actually. But there's a general conjecture about this kind of thing in any semi-simple Lie groups. Okay. And another example is that the one unsolved Thurston conjecture is virtual Haken conjecture. So the virtual Haken conjecture tells you if you take a finite cover of some closed hyperbolic 3 manifold, then the first Betti number is always bigger than 1. So the H1 is infinite. That's a virtual Haken conjecture. This is true for arithmetic lattices somehow. Except, am I wrong? Yes, there are some exceptional cases, but by Lobochiki, I think in SON1, except few cases, this virtual Haken conjecture is true. So if you take some arithmetic hyperbolic n manifold with some exception, go up to some finite cover, then the first Betti number is always bigger than or equal to 1. So arithmetic lattices has a huge symmetry. And somehow, these symmetries enables you to do a lot of rich geometries. Okay, so this is a propaganda for arithmetic lattice that you can hear more about from Alain. So I finished my job on arithmetic lattices. So what's left? So there's some time left, I think like 15 minutes. So let me go back to some deformation theory groups. But surface groups, it has a rich deformation theory in any semi-simple Lie groups. I already mentioned about this. The strictly convex projective structures. Okay. This is basically a representation into SL3R, in general like SL and R. Yes?
That's one question about your last statement. What does curvature mean?
It's not a curvature, co-volume, sorry. Co-volume.
Oh, sorry.
So if you quotient out H to R by this lattice, then it has a volume less than or equal to X. It has an exponential growth. So for the remaining time, I briefly mention about some deformation theory of the surface group. So I think this theory is developed from Toledo. So what's the Toledo thing? So Toledo, he used some Kähler form in the target manifold to study the deformations of some surface groups. So let's take a representation from the surface group into any actually Hermitian symmetric space. Okay? Then this representation gives rise to row equivariant map from the universal cover of the surface to the symmetric space associated with this Lie group. In our case, this is complex hyperbolic space. Okay, omega is a Kähler form. So this is a Kähler. Okay. So generally, it is known that there's some restrictions, but if this representation is reductive, meaning if the image is a reductive group, Zariski closure is a reductive group, then you can find harmonic row equivariant map. Okay? Then you can pull this guy, pull this Kähler form to here, and because everything is row equivariant, you can make it descend onto the surface, and you integrate it. And there's some normalization constant here. And this belongs to actually integer. Okay. This belongs to the integer, ranging from actually the image range from Euler number and minus Euler number of the surface. Okay. So as long as this target space has some form, actually this is the pullback is if you construct a flat bundle out of this representation, This is some characteristic class, and the value belongs to this integer. So if the value, this is called Toledo invariant. If the Toledo invariant is maximal, then it is say rho is maximal. Rho is maximal. If the invariant, if it attains these things. Okay. And it turns out that these maximal representations are very rigid, actually. Very rigid. And recently, there's a group of people studied this thing. They showed a generalization of this theorem. Because this is a characteristic class, this value is constant on the component of the representation variety. Okay? They showed this kind of a statement. Take a representation of the surface group in a Hermitian symmetric space. Such that with maximal Toledo invariant. Okay. So somehow this maximality guarantees you that the image of this representation, so this always Zariski dense, Zariski closure. This is a semi-simple Lie group associated a tube type Hermitian space. So what is tube type Hermitian domain? It looks like this. It's the simplest example is our favorite one, upper half space. So PSL to R. So this domain is like this. You take a real line here, and this is IC. So IC plus R belongs to R2. Let's say C. So it looks like a tube. It looks like a tube. In general, you take Cn. Okay. So among the Hermitian type symmetric space, there are a special family of Hermitian symmetric space, which is called the tube type. And they proved as long as this number, this invariant is maximal, the image got stuck inside some tube type Hermitian space. So this is a generalization of this Goldman-Wilson type rigidity things, actually. And there's a sort of a converse statement to this deformation theory also. Let me state this sort of converse statement and try to explain some ideas. So take any representation conversely, not exactly conversely, but Now this is not a Hermitian, it's a general semi-simple Lie group. It's a general semi-simple Lie group. So target is a general semi-simple Lie group if, let's say, reductive. Reductive means the image, i.e. Zariski closure is a reductive group. We have to apply some Simpson theory. Then the Simpson theory is developed under the fact that the representation is reductive. In reductive case, you can deform the representation actually, so it doesn't matter. But to simplify the statement, let's assume the image is reductive. So if rho cannot be deformed, to a Zariski dense representation, then the image is a tube type. It's inside the tube type Hermitian space. Okay. So their theorem tells you if the invariant is maximal, then the image lies in some special type of Hermitian domain. This theorem tells you if we cannot deform it to a Zariski dense one, then actually it lies inside the subtube type Hermitian semi-simple Lie groups. Okay? Somehow you cannot escape this tube type Hermitian domains. So this means that some factor, because this semi-simple Lie group, some factors of this G, actually G could be just a reductive group, then some Levy factor of this guy should contain this tube type Hermitian semi-simple Lie groups. Okay? So the idea is simple to prove this thing. If you have an abelian subset in Lie algebra, okay, if you have an abelian subset in Lie algebra, you can do the root space decomposition. Okay. You decompose the Lie algebra into the root space. For example, in SU21, if you decompose it in, how many roots are there? There are 2 or 3, I think. There are 2 or 3. So in this case, one can work it out actually explicitly using some standard hyperbolic isometries. You decompose the Lie algebra into root spaces. And each root space is invariant under this action of the representation. Then you can, because then you can associate some symplectic form actually coming from the Lie algebra, symplectic forms. And you can define the invariant. Actually, that's the first Chern class of the flat bundle arising from this representation. So each factor you have some symplectic forms, and it gives rise to some invariant. And then you analyze things using like Simpson theory and so on. Then finally, you end up with this conclusion. If we cannot deform it, it always got stuck inside this cube-type Hermitian domains. And somehow the surface group representation is very fascinating. I mean, there are theory developed by like Labrie and using some cross ratios, and there are different types of theory developed by different people in surface group case. So this is another propaganda to study surface group representations. Maybe it's a good time to stop here. You have any questions?